record this session. So as I said before, you have to submit only Excel chapter 6. So you go to module 3, you go to the normal distribution, and you download the file. So you do the file, and then there are gonna be 3 different spreadsheets. So just replicate what we did, and then include this part of the central limit theorem and what we're gonna do tonight about the binomial distribution, and then you will be fine, okay? So you will be earning extra points. As I said, probably 2 points, 3 points might be given to students who complete that assignment. And remember, 3 points is almost like 1.5 Excel spreadsheet, okay? Or 1.5, or it's almost half of the credits that you get for a full problem set or for the exam. So 3 points are gonna be very good for anybody who wants to do the extra work, okay? Is this clear for everybody?
Yes.
Okay, so thank you for responding. So just like a reminder what we did last class. Thank you. So so remember, we are going to use the central limit theorem. We're going to make assumptions, very strong assumptions, based on population information, and we're going to be able to do this as samples. So we once again, we are assuming that we have a population where we know mu and sigma. So the mean, the population mean, and the standard deviation of the population. So and then we start taking samples, these repeated samples. We take one sample and take the mean of this sample, a second sample, take the mean of that sample. So we take so many. So at the end, we are gonna take the mean of the means. So that gives us a distribution that is known as the mean of the sample means. So where we can measure, so we can use that information to assume normal distribution and find the area under the curve when we are using samples. So in this case, we're going, hello? Let me mute all. Okay. So so what we are gonna do is we are gonna assume, so this is a very interesting assumption. So we are gonna use population data. So we are gonna assume that the mean, the mean of the sample means. So all these, the mean that we obtain from taking the mean value of the means that we calculated from repeated samples. And then we're gonna assume that this mean is gonna be equal to the population mean, right? So I don't have to make computations if I have the population mean and I'm using a sample. So I'm gonna assume that that sample has the value of the population mean. And then to compute the degree of variation, so I'm gonna use the standard error. So that standard error is gonna be based on the value of my sigma divided by the square root of the sample size. So that is very important because here we can use a sample and the sample size is gonna account for the for the sample. So if we were using only population data, we use the standard deviation alone. But because we are using a sample, we are gonna use the standard error. And remember the standard error, which is sigma x bar. So this sigma x bar is gonna be known as the standard error, and it's gonna be the regular sigma that we know from the population divided by the square root of the sample size. So in this case, we have population data, right? So this is the population data. At some point, the US Department of Transportation conducted a big data collection, and they know that in average, people from who are 15 to 19 years old, they used to drive 25 minutes, 24 minutes, 54 minutes if they are people between 20 and 24. So 64 minutes if people are from 25 and 54. So those are data, this is data that was collected from a big sample and can be representative of the population. So in this case, we pick a sample of 50 drivers. And the question is, if you have 50 drivers, how likely is that if they are between 15 and 19 years old, how likely is that they are going to be spending between 24/7 and 25/5? So remember, here the case is we have a mean of 25 minutes. So my question is, how can I make it? So what is the likelihood if I have 50 drivers, they are going to be driving between these times? And we are assuming that we know the population standard deviation. So remember, based on this population data is known. So we can use this population data and apply it to my sample size. So that's the reason it's very important for me to know the sample size. So once I know the sample size, I'm going to be able to apply this formula, this C-score, apply the normal distribution to a sample size that is big enough. And remember, the magic number here is going to be 30. So any sample that is 30 and bigger, so can be considered for normal distribution. So in this case, so we are going to use, and remember here, so what we have to do is something that we already know. So we are going to find the C-score, and this C-score is going to be based on my random variable. So in this case, 24/7 and 25/5 minus the mean of the sample mean that happens to be the population mean. And then we're going to divide this by the standard error. So remember this standard error, we have a formula here that tells me what is the standard error, okay? So that's what we're going to do. We're going to find the difference between the observed and the hypothetical mean. So this is the random variable and the hypothetical mean, and divided it by the degree of variation. In this case, the degree of variation is going to be sigma, but because we are talking about samples, it's going to be the standard error. So that's what we did here. So this is my normal distribution. So I'm assuming normal distribution. So I don't need to compute the mean of the sample means, because I am assuming, I'm making this big assumption that that mean is going to be represented by the population mean, and my degree of variation is going to be sigma divided by the square root of the sample size. So in this case, my variation is going to be represented by 0.2121, not by 1.5. So this 0.2121 is accounting for the size of the sample, okay? So we did it. So we computed the C-score for these two. Well, according to this, we computed the C-score, we found the C-score, and then we found the area to the left. So in our case, we don't have to do that because we already computed. So here, all I need is the mean of the sample means, which happens to be the population mean. We have the standard deviation, we have the sample size, and we obtain the square root of, we obtain the standard error by dividing the by dividing sigma by the square root of the sample size. So this is my standard error. So remember that here we are computing the area under the curve that is to the left of 24.7, which is the first point, and the second is going to be 25.5. So we computed those values, and we used the normal distribution function that is asking me for the mean, so this is the mean. So sorry, it's asking me for the x. In this case, is 24/7, and then it's asking me for the mean, which is 25, and then it's asking me for the standard deviation. But remember, I'm not using the standard deviation because I'm not computing population data. I'm computing data that is based on a sample. So that's the reason I am using the standard deviation instead of the sigma, right? So we computed that values, and then we did the same for 25.5. So we found that there is a 91.2% likelihood that young people are going to be driving within these values. So remember, this is the standard deviation. How many standard deviations do we have here? So so this 24/7 is located to minus 141 standard deviations to the left, and this 25.5 is located to 2.36 standard deviations to the right. So we are going to be able to compute those values and find the area under the curve. So that's exactly what we did before. So remember, you can do exactly the same if you want to measure the area to the right, the area to the left, or the area between two standard deviations. So at the end of the slides, I made a reproduction of what you have in your Blackboard portal. So you want to find the C-score, you use the standardized, you want to find the area to the left, to the right, between two different values. So you can go back and forth and find all these values, okay? So this is very easy. So once again, we are making a big assumption that we are assuming normal distribution. And once again, we are gonna be able to use samples that are 30 and larger and make that assumption applying the central limit theorem. But that is not the only beauty of the normal distribution. We also can do this with the binomial distribution. So we can do a normal approximation to a binomial distribution. So remember, the binomial distribution is a distribution. The normal distribution is used to approximate the binomial, when it would be impractical to use the binomial distribution to find a probability. So remember, so let me just bring that to you. So if you remember the formula for the binomial distribution formula. So remember, it's kind of complicated. We have to do all these steps. Just imagine, do this for 100 different times. So we also can create a table. The table can be good, but we can avoid all these pains if we kind of forget about this formula and we assume normal distribution. So we have to meet some of the requirements that the normal distribution, this approximation, is asking me to consider. So in order to do the normal approximation to the binomial, so remember, there are some requirements for the binomial. We have two different possibilities. One is P, the other one is Q. So the trials are independent and they cannot change. So that means that they cannot change. So the value of P is going to be the value of P all the times, and the value of Q is going to be the value of Q all the times. So so that is the independency of the trials. So we are talking about independent events. So so those are some of the considerations that we need to think about. But also, once we have once we know that this binomial experiment is truly binomial, we have to check for two things. So the first thing is that if I multiply the sample size times the probability of success, that number has to be 5 and higher. The same thing for the probability of failure. If I multiply the probability of failure times the sample size, that number has to be higher than 5. If any of these number is lower than 5, we cannot use the normal approximation. So that means that we have to do it by hand, probably using Excel and building the tables. But for example, if you can build a table and make the table make sense when you have, for example, 20, 30, no more than 30 different trials. So just imagine that you have 150. So it's going to be a big table, a big graph. You can avoid that by assuming normal approximation. So once we make sure that this normal approximation is good, so we have values that exceed 5 or at least 5. In both cases, we are able to compute the mean and the standard deviation. So remember, in order to find the area under the curve, we need sigma and we need mu. So in this case, we can use the normal approximation because this is true, this is true. So we can proceed to compute mean, the population mean and the population standard deviation. So here, N is the number of independent trials, P is the probability of success in a single trial, and Q is the probability of failure in a single trial. So that sounds very simple. So you have mu, you have sigma, all you need is a random variable, so you can compute your normal distribution, you can use the C-score, and you are gonna be able to know the area under the curve in this case, right? So so that sounds very simple, but it's simple, but it has, after all these things, we have an additional requirement to fill. So that is gonna be the following. So that's gonna be the following. So remember, the binomial is a discrete distribution. So we are using a histogram, and the normal is a curve. So when you fit the curve on the binomial distribution, you can see that these areas are not included in our computation, right? So we have to account in some ways for this area under the curve. This area that is beyond the normal curve. So the binomial distribution is discrete and can be represented by a probability histogram. To calculate exact binomial probabilities, the binomial formula is used for each value of X and the results are added. So what is going to happen here, to make the long story short, let me keep doing this. So we are going to make a little adjustment to this, right? When you use a continuous normal distribution to approximate the binomial probability, we are going to move 0.5 units to the left or to the right. So from the midpoint. So we can include all the possible X values in the interval. So that adjustment that we are going to make to the left or to the right is called the continuity correction. Let's go back to our portal. That I also put it in my in the slide at the end. Remember, I said when you are doing your homework, keep this very, very handy. So we're going to be using this in order to solve what is going to happen. Do we have to subtract 5? Do we have to add 5? I don't know. But with these guidelines, we can make some adjustments, right? So we know how much we have to adjust in order to make the continuity correction or correction for continuity. Okay, so let's see an example. So in this case, we have to add or subtract 0.5 depending on what the problem is asking me to do. Okay, so let's see an example. So use the continuity correction to convert the binomial interval to a normal distribution interval. So the probability of getting between 270 and 310. So all of them are inclusive. So what does that mean? So that means that, let me open this. We are going to have the following new document. So we are going to have the following. I don't need this. This is personal. Let me make this smaller and get it off your way. So what we have here is the following. I mean, I don't know the mean. So I'm just going to draw this. So just imagine that we have our binomial distribution, right? So something like this, right? I'm not very good at drawing things, but just imagine that this is our binomial distribution, right? So basically, I'm gonna fit a normal to the binomial. So it's very clear that some of the areas here are missing. So the rule says the following. In order to find the area under the curve for 2 and make this correction, just imagine that this is the mean. I don't know what is the mean is, but I have mu here. So I have 270. And here is 310, right? So the area that I'm gonna be computing is gonna be the area that falls between these 2 points, right? If you are following, you can see that this is the area under the curve. So because we are fitting this normal distribution curve on top of a discrete distribution, when we are looking for the adjustment between 2 different points, we are gonna subtract 0.5 to the left, and we're gonna add 0.5 to the right. So that basically means when I am computing the C-score for these values, I'm not gonna use 270. I'm gonna use 269, sorry, 0.5 minus mu, which I don't know what is the value, divided by the standard error, right? So that's what I'm gonna do. So remember, the standard error is gonna be sigma divided by the square root of the sample size. So that is gonna be one of the values when I have 2 different, when I am looking for the area under the curve. So I'm gonna be subtracting 0.5 to the left, adding 0.5 to the right. So the second C-score, I'm gonna use C equal to, so this is 310, I'm gonna add 0.5. So this is gonna be 310.5 minus mu, I don't know what is mu, but it should have a value, divided by the standard error. Sorry for the right. So that's what we're gonna do. So this is rule number 1, when you have to find the area under the curve between 2 different random variables. So you are gonna subtract 0.5 to the left and add 0.5 to the right, and then you are gonna be able to compute the area under the curve. So the probability that X is gonna be between 269.5 and the probability that is 310.5. So it's gonna be the value of this area to the left and the value of this area to the left. So we are gonna proceed as we know, right? Is this clear for everybody? So I hope it's clear. So one of the things that we have to do when we are using the binomial, so once again, is to correct for continuity. So in this case, the only trick here is that we are gonna, when we have 2 different random variables, we're gonna subtract 0.5 to the left, we're gonna add 0.5 to the right, and we are gonna proceed to compute the values. So in this case, what I will do, well, we don't have a mu here. So so we are gonna leave it alone for the time being. So let me see if I can make this. So this is the first case, right? So we have the probability of getting between 270 and 310 and successes inclusive. So the discrete points values are between 270, 271, all the way up to 310. So if we want to adjust for continuity, we are gonna be adjusting, as I said before, 0.5 to the left plus 0.5 to the right, okay? So that's rule number 1. What happens if I want to know the probability of getting at least 158? So that is a very good question. So the probability that X, what did I do? That X is at least remember, is greater than equal to 158. So the question, what do we do? Do I subtract? Do I add? So here, this is telling me that I have to subtract. How do I know? Well, I didn't know. I am just looking at the result, but I don't know for sure. So remember, at least means 158 inclusive, 159, 160, and all the way up. Remember, when we use at least, we are including the number, and it's going to be that number and higher. So what I'm going to do is I am going to go back to my, well, probably I'll go to my last slide, which is closer. So when I have at least, what should I do? Well, it tells me that I have to subtract 0.5, right? So this table is very handy because at this point, I'm looking at the example, but I don't know for sure what to do, right? So in this case, I'm gonna compute the probability that X is less than 157.5, right? Because based on my table here, I know that when I have this greater than equal to, which means at least, I have to subtract 0.5. So when I am computing my C-score, I am gonna do the X, which is gonna be 157.5.
Professor?
Yes, sir.
Should it be X is greater than?
Say that again, please.
Should it
Oh,
be X is greater
that's, thank you, yes. Thank you very much. That's a very good point. Greater than 157. Thank you. That is absolutely right. So we have mu. I don't know if I mentioned the mu, and then we are gonna divide by the standard error. Thank you very much for catching that. I was just checking whether you guys are paying attention. So we are gonna find the area that lies to the right of 157.5, right? So if I had a graph here, so what I'm gonna do is I have my normal distribution. I don't know mu. So this is mu. I don't know if this number is to the left or to the right. Let's say that is here. So this is 157.5, right? I'm gonna compute the, oh, sorry, that is horrible. I'm gonna compute the area to the right, right? So I find those values, I find the C-score, and then I find the value that corresponds to the area to the right. So my point is very simple. We have to look at the table because I don't know whether I have to use the right, the left. This is a little bit tricky because what happens if you want to know the exact value of a random variable, right? So what is, like, for example, we have this case where, well, in this case, this is the probability of getting at least 158. So we are using, we are correcting for continuity, and we are gonna use 157.5. So we are gonna do this example. But in this case, well, that example is basically this one. So when you have to find the exact value of a random variable. So let's do this because we have many cases. So I didn't put here the case where we have the value between two random variables, but remember that if you have the value between two random variables, you have to subtract 0.5 to the left and add 0.5 to the right. So in this case, what happens when we want to know exactly the value of a random variable? For example, in this case, let me make this smaller. And let me bring my Excel table. So I did the binomial here. So how do we find those values? I mean, this is very simple. We are going to be doing the following. We are going to collect the data that is necessary for us. So in this case, so I set here the conditions. So those conditions are going to be very important, because if these numbers are greater than 5, then we can proceed with the binomial, with the approximation to a binomial probability. But if these numbers fall below 5, we cannot do that. So in this case, a survey reports that 62% of the internet users use Windows Internet Explorer. Just imagine how old this example is as their browser. So very few people use the Internet Explorer, as far as I know. So you randomly select 150 internet users and ask them to use the internet, whether they use Internet Explorer as their browser. So what is the probability that exactly 96% are gonna say yes? So, exactly the person 96 is gonna say yes. So in this case, this is a very particular case, because, so we are gonna try a couple of them. So in this case, the probability of this is 62, so it's 0.62. So the probability of failure is gonna be 1 minus my probability of success. And in this case, we have 150 people. That's our sample. As you can see, I already set up these equations here. So I multiply n times p, n times q, and I found that these numbers are way higher than 5. So can I proceed with my normal district approximation? The answer is yes. So then the second step, as you might remember, so once we get the numbers, so we can proceed. Once we confirm that we can proceed to the normal approximation, we compute the mean and we compute the standard deviation. So that's what I did here. So I multiply n times p, so that's my mean, and I computed the standard deviation n times is the square root of n times p times q. So what do we have here? Well, basically what we have here is the following. So without much of the information, I can approximate this to the normal. I don't have to draw the binomial because I don't need it. So in this case, I know that my mu is here, which is equal to how much? 93. My sigma is going to be equal to, in this case, 5.94. So here, as you can see, I took the square root of b times 2b, the square root of p, q, and n. So I multiplied them and took the square root, and this is my normal, standard deviation. So here, my standard deviation is going to be equal to 5.94, right? So now the question is, what is the probability of exactly 96? So 96 is going to be somewhere in here. So my x here is going to be 96. So what is the probability that the 96 person is going to say yes? So in order to solve this, we are going to apply the continuity correction. So we are going to build an area around my 96. So I'm going to subtract 0.5. I'm going to add 0.5, right? So in this case, what I'm going to do is the following. I am going to, my x1 here is going to be 95.5. And the other, so this is 95.5, and this other one is gonna be, hold on, I made a little mistake. It looks like very simple, but has its own, so this is the 96. So here is this, here is the other one. So what is this part, what is missing, right? So in this case, we have to find, according to this, we have to subtract 0.5, add 0.5, and find the area under the curve, right? So that is gonna be exactly 96. So in this case, what I'm gonna do, so for my x2, so the second point is gonna be 96.5. So the probability that x, in this case, is gonna fall between 95.5 and 96.5 is gonna be computed as follows. So we are gonna take the C-score of 95.6, 95.5, 95.6, and we are gonna subtract those numbers. So let me put this probably here. So here I'm gonna find the probability that x is less. In this case, I am gonna measure the area to the left of 95.5. And then here, I'm gonna measure the probability of x that is less than 96.5, right? So I'm gonna use the norm that is, so I'm gonna use my 95.5, so that is x. My mean is 96, I'm gonna type it, and the standard deviation here is gonna be, hold on, so do we need, so this, the standard deviation is gonna be 594, right? 5.94. And then I'm gonna say true because I want the cumulative area, right? So I have the area to the left, and then I'm gonna do the same norm that this. I'm gonna use the second value, 95.6. I'm gonna use the mean, which is 96, and the standard deviation that is 5.94, and then also true. So then in order to find the area under the curve, so the probability that is gonna be exactly 96, which is gonna be defined by this area, is gonna be the largest minus the smaller, and that's gonna be the probability that the 96% is gonna respond yes to that particular question. So this is exactly 96. So when we have this, that is more than 100. So remember, more than, I don't know, let me go back to my table. When I see more than, so I have to add 0.5. I don't want to do more, like for example, in this case, more than 100. So we have a, so the same thing. So we have the mean, which is 93. According to my computations, we have a sigma, which is equal to 594. And now I'm gonna find the area under the curve that is greater than 100. So I'm gonna measure the area to the right, right? So we can, so in order to find that area, remember, so we have to go back and look at the table. So it's gonna be when we are using more than, so I have to add 0.5, right? So in this case, my number is gonna be 100.5. So here, I'm gonna find the area under the curve for x equal to greater than 100.5, right? So what should we do? So in this case, we are gonna use, because we are using the area to the right. So, and this 105 is gonna give me the area to the left. So what I'm gonna do is equal 1 minus norm.dist. I'm gonna use the 100.5 as the x. The mean is gonna be 93, which is this number that we compute here. Here, 93. Then I'm gonna use 5.94 as my standard deviation, and then true, right? So that is the area to the right. So we are doing exactly the same. So in this case, more than 100. So at most, I'm just gonna present these two last numbers. So at most means that I have also to add 0.5, right? So at most means that 85 and less. So 85 is included, but it's gonna be 85 and less. So in this at most, I have to add 0.5. So I'm gonna find that my x is gonna be equal to 85.5. So you can compute this area less than 75, less than, I have to subtract 0.5. So it's gonna be 74.5, right? So if it says less than, I have to subtract 0.5. So I'm gonna find this area for 75. So adjusting for continuity, the number I should use is 74.5. And at least means 97 and more. So that means exactly that we are gonna subtract 0.5, right? So the number of 97 is gonna be 96.5, right? So you can compute these numbers and add it to your homework, and that's gonna be the case. So is this clear for everybody? Is there any question? Are you guys there? Are you sure that you are not sleeping?
Yes, I'm sure.
Did
got-
I catch you sleeping during the class?
I got one question.
Yes, please, Adam.
The recording for 6, I don't see it.
The what?
The recording, the class recording
Oh,
for chapter 6.
Oh, per chapter 6 is there. I think I just put it on. Hold on. So so this is just the last class, and this is the 3 normal distributions. So the central limit theorem second is the one that we are doing now. So this is open already.
Okay, I see it.
Okay. Yeah, I think probably you didn't see it because I just put it on today. Sorry. So let me stop the recording. So is there any question, guys?